Hi, this is our presentation on smart grid implementation and electrical infrastructure modernization. First, I'll be going over the flow of the presentation and the contents within by introducing the problem and providing background on how current grid systems operate, then examining the limitations of legacy grids and their impacts, our proposed design and system architecture, moving to our methodology and supporting analysis, and finally, discussing the results, implications, and final verdict. The goal of this project is to modernize electrical grids for renewable integration. And this is because solar and wind output changes based on the weather and the time of day. And currently, modern systems are built for constant power, which leads to challenges in supply and demand and overall reliability. A little bit of background, electrical grids are built around centralized generation systems, where large power plants generate electricity and sent across long distances. Power moves through transmission lines, through networks, and then to us, the consumers. The grid is built around steady power outputs, where rates are predictable and supplied power is planned in advance. Now we'll explain the key limitations of traditional grid design.
All right. Thanks, Rain. Appreciate that input there. So I'm going to continue from my part, which is the main problem statement of the presentation. So we're going to start off with the legacy grid constraint. So most modern electrical infrastructure still operates on legacy radial distribution models. In this conventional architecture, power flows unidirectionally from centralized substations directly to end users. The core limitation of this passive system is a complete lack of real-time observability. So utility providers have no native data feedback mechanisms to monitor localized grid conditions or equipment failures at the distribution level. So highlight that the flow moves strictly, in order to highlight this, that it moves strictly from left to right, from the centralized plant through the step up or step down, depending on what's needed, directly to the consumer. Because power only flows one way, data does as well. So there are no arrows pointing back to the generation side, meaning utility providers have no real-time data from those distribution nodes. So next, we're going to go on to like the impact, the operational impact, and the modernization gap. So for this, because of this operational blindness, the grid is highly vulnerable to prolonged power outages and inefficient energy distribution. Furthermore, traditional passive protection equipment struggles to handle the complex bidirectional power flows introduced by DERs or distributed energy resources and rising EV charging loads. So, to resolve these inefficiencies, there's a critical need to modernize the network into an active cyber physical system by integrating a two-way communication layer, specifically using advanced metering infrastructure and distribution automation.
So the whole problem we're solving here starts with a legacy grid. Right now, most electrical power flows in one direction, that is from the substation to your house. And that's it. There's no feedback, no real-time data. What we're proposing is a shift to a smart grid by combining the three elements on the screen. The first is the AMI, which replaces old electromechanical meters with digital smart meters that measure voltage, current, and power quality continuously. The second is DA. Intelligent devices and automated switches are installed along the distribution lines that can monitor and react to any grid conditions and changes without waiting for a human to step in. Lastly, we have energy storage on any excess power not being utilized effectively. We will focus on this quite a bit, and that's where all our data is. Let's talk about the methodology and engineering process. Integrating AMI and DA requires three core systems working together. Firstly, two-way communication protocols. AMI replaces the old passive billing model by enabling dynamic pricing during peak hours through bidirectional communication from consumer to distributor and vice versa. Secondly, an automated fault response algorithm will be implemented. When a fault occurs, line sensors pinpoint it, automated reclosers isolate the damaged section, and the system rewrites power from adjacent areas to restore service. All of this is done without any human intervention whatsoever. Third, excess power storage. Any surplus power being redirected through the network needs somewhere to go. The storage technologies best suited for this are covered in the following slides. Together, these three systems are what make a truly responsive, self-healing smart grid possible. This table compares 6 energy storage technologies. We'll only focus on a few key ones. Technologies like pumped hydro and flywheels are most common today. Flywheels offer high efficiency and fast response time, while pumped hydro scales to thousands of megawatts at very low cost per kilowatt hour. Hydrogen fuel cells and gravity rail systems are still developing or at concept stage. They promise very large scale, very long duration storage, but come with high capital costs and lower round trip efficiency, which will hopefully be reduced with further research. The bottom line, the best technology depends on the use case: speed, scale, duration, or cost.
So for this analysis of data, renewable energy sources are inconsistent for supply and demand. Energy storage systems solve that issue to store and reuse energy when needed, improving grid reliability. Even with the storage solution, different technologies have timescales. So batteries are short term, pumped hydro is medium to long term, and hydrogen is long term. Energy storage is essential for renewable energy systems to be reliable and usable at different scales. So for the storage comparison, batteries give fast response and they're great for short-term solution. And for hydrogen, they're great for long-term storage and they're low efficiency. For pumped hydro, high efficient and large capacity while being geographically limited. And for thermal, they're cheap while being less efficient for electricity generation. So each has their strengths and limits. No single system will solve every problem. And for our error analysis, so for a battery, our thermal runaway and degradation. For hydrogen, significant energy loss and conversion. For pumped hydro, geographic specifications and high build cost. And for thermal, we have heat loss and low efficiency. And in engineering designs, they must list different trade-offs ranging from safety, cost, performance, etc. And last, for amplifications, energy storage allows for stable and reliable renewable energy systems. The reduction of fossil fuels equals our climate goals. The most effective solution is a hybrid of multiple technologies into a system. The solution for efficient storage challenges for the BBC Grand Challenge of sustainable and reliable energy systems is critical.
By taking everything into account, our main objective is to modernize smart grid systems to support current and future renewable energy resources, to transition from current smart grid systems into active cyber physical systems. In order to do this, we use two types of technology, one being the advanced metering infrastructure, or the AMI, and the second being the distribution automation, or the DA. And we also implement energy storage to basically just store any excess power that we may have. And so for the AMI, it is basically just a two-way communication. And for the DA, or the distribution automation, we basically utilize a fault location, isolation, and service restoration algorithm to basically utilize line sensors to reroute power and to restore service. And so the final verdict is, does this solution solve our problem? And yes, it does. But it could have some improvements. Improvements like using artificial intelligence as a whole, or to use hybrid storage systems, which is basically just combining a bunch of storage systems into one and using the pros of each one to create the most efficient one, as smart grid systems are a necessity and need to be implemented all around the world on a global scale. And here are our references, and thank you for listening.